welcome back to another new video. Here we'll discuss about steps to reduce quadratic form to normal form by orthogonal transformation. So reducing here we need steps to understand to reduce the quadratic form to the normal form by orthogonal transformation. First step comes as write the symmetric matrix from the given quadratic form. So in previous video we have discussed how to convert quadratic form to symmetric matrix and symmetric matrix to quadratic form. So in the same way you need to convert the quadratic form to the symmetric matrix. Find the eigenvalues of A. So as we did after getting the matrix, we had to find the eigenvalues of A, then find the eigenvectors corresponding to eigenvalues of A. So eigenvectors also should be found, and find the normalized eigenvectors, that is x1 by norm x1, x2 by norm x2, x3 by norm x3. So for example, if x is a variable matrix like x, y and z, norm x comes as under the root of squares of these elements as x square plus y square plus z square. So this is what norm x. So in this way, x1 by norm x1 and x2 by norm x2, x3 by norm x3 called as normalized eigenvectors. And next you need to find out the normalized model matrix P. So model matrix P, there we find only we write only the eigenvectors, but normalized model matrix is nothing but we have to write these normalized eigenvectors in the form of matrix as x1 by norm x1 and x2 by norm x2 and x3 by norm x3 as a column wise. Then next, check all the three eigenvectors are pairwise orthogonal or not. So pairwise orthogonal is nothing but x1 into x2 transpose. So when we multiply two eigenvectors, we have to get the 0. So first, for example, if we take a first eigenvector into transpose of second eigenvector, that should be given as value as 0. Then x2 into x3 transpose, it means second eigenvector into transpose of third eigenvector should be equals to 0. So in this way it has to satisfy these three conditions. Then we can tell this that eigenvectors are pairwise orthogonal. So we have to check whether they are pairwise orthogonal or not. Write the P transpose, then P transpose A into P is equals to D. We know this model matrix transpose of that we need to write. Then after P transpose A into P is equals to diagonal matrix D. The orthogonal transformation X is equals to Py, which transforms the given quadratic form to canonical form or normal form. So this is what orthogonal transformation, and that transform the X is equals to Py to quadratic form, that to canonical form and normal form. So these both words mean the same. And next, the final step comes as y transpose dy is equals to, so lambda 1 y1 square plus lambda 2 y2 square plus lambda 3 y2 square. So when we multiply these three matrices, we get the final as this, where lambda 1, lambda 2, lambda 3 are nothing but eigenvalues, and here where D is diagonal matrix of we write the eigenvalues in the form of diagonal matrix lambda 1, lambda 2, lambda 3. So at last you will get this final matrix. Here we go with one problem. Reduce the quadratic form 3x square plus 2y square plus 3z square minus 2xy minus 2yz to the normal form or canonical form by orthogonal transformation, and hence write its rank and index, signature, nature and transformation. So here we have to reduce this quadratic form to the normal form or canonical form by orthogonal transformation. And here, so given quadratic form is 3x square plus 2y square plus 3z square minus 2xy minus 2yz. Now from this quadratic form we have to write the matrix that comes as a symmetric matrix. We have discussed in previous video that how to find the symmetric matrix from given quadratic form and finding quadratic form from given symmetric form. So here the matrix A is 3 minus 1 0 minus 1 2 minus 1 0 minus 1 3. It comes a matrix as this. Then characteristic equation of A is in the form of determinant of A minus lambda I equals to 0. So here lambda will be subtracted from the diagonal elements and we get it as 3 minus lambda minus 1 0 minus 1 2 minus lambda minus 1 0 minus 1 3 minus lambda, and the determinant of this matrix is equals to 0. And the final will be of the cubic equation, as this is the 3 by 3 matrix. It will be of the form lambda cube minus s1 lambda square plus s2 lambda minus s3 equals to 0, where s1 nothing but trace of the matrix, it means sum of the diagonal elements, 3 plus 2 plus 3, that gives us 8, and s2 nothing but minors of the diagonal elements, and it comes as this. When we find out the determinant s2, we get it as 19. Comes as it is the determinant of the matrix A, and the determinant is 12. Now substitute s1 s2 s3 in the equation. You get it as lambda cube minus 8 lambda square plus 19 lambda minus 12 equals to 0, and by using calci get the values of lambda. We get the values as 1 4 and 3. I am taking 1 as lambda 1 and lambda 2 is equals to 4 and lambda 3 equals to 3. So here we need to find out the eigenvector for each eigenvalue. Then case 1, put lambda equals to 1 in this characteristic equation. So this is a characteristic equation. 3 minus lambda minus 1 0 minus 1 2 minus lambda minus 1 0 minus 1 3 minus lambda into variable matrix xyz and it equals to constant matrix. And here when we subtract this, when we put lambda equals to 1, 3 minus 1 becomes 2 and 2 minus 1 becomes 1, 3 minus 1 becomes 2. So this comes as a matrix. Now write the equations from this matrix. As from first row we get it as 2x minus y equals to 0. Let it be as equation 1. From second row we get it as minus x plus y minus z equals to 0. That let it be as equation 2. And from third row we get it as minus x minus y plus 2z equals to 0, and let it be as equation number 3. Solving any two of the equations we get which gives the values of x, y and z. I am solving the equations 1 and 3. So x, y, z. First take the y coefficients minus 1 and minus 1, and then take the coefficient of z. In first equation coefficient of z is 0. Then take the coefficient of x as 2. Then again take the coefficient of y, that is minus 1. Now from same third equation we take the coefficients, you get it as minus 1 2 0 and minus 1. Now solve this. X by minus 1 into 2 minus 2 minus 0, that equals to y by 0 minus 2 into 2 4 minus 4, and z by 2 into minus 1 minus 2 minus 0. Then x by minus 2, y by minus 4, z by minus 2. So when we divide it by 2, we get it as x by 1, y by 2 and z by 1. So x1 nothing but eigenvector. First eigenvector you get it as 1 2 1. So this is the eigenvector for eigenvalue lambda equals to 1. Case 2, put lambda equals to 4. So when we put lambda equals to 4 in that characteristic equation, you get it as minus 1 and next diagonal element minus 2 and third diagonal element minus 1 multiplied by variable matrix equals to constant matrix. Now write the equations from this matrix. Minus x minus y equals to 0 is equation 1. Minus x minus 2y minus z equals to 0 is equation 2, and minus y minus z equals to 0 is equation 3. Now solve any two of the equations to get the values of x, y and z. I am solving here equation 1 and equation 3. Then x, y, z, similarly taking the coefficients of y, next taking the coefficients of z, taking the coefficients of x, and again taking the coefficients of y. So you get at this. This is from first equation and this is from second equation. Third equation. Then x by minus 1 into minus 1, 1, and 0 into something is always 0, equals to y by 0 minus of minus 1 into minus 1 is plus 1, and when it is multiplied with minus it becomes minus 1. Then that equals to z by 1 minus 0. Then x by 1, y by minus 1, z by 1. Then x2 is a second eigenvector, and we got it as 1 minus 1 1. So this is the eigenvector for eigenvalue lambda equals to 4. Now take case 3, put another lambda value, eigenvalue, that is lambda equals to 3. So when we substitute this lambda value 3 in the characteristic equation, you get it as 0 minus 1 0 minus 1 minus 1 minus 1 0 minus 1 0, and multiplied by variable matrix that equals to constant matrix. So now write the equations from this matrix. Let it be as equation 1 and 2 and 3. So by solving the equation 1 and 2, you get these values, coefficient of y, x and z, and at last again coefficients of y. Then on solving we get x by 1 minus 0, y by 0 minus 0, z by 0 minus 1, that is x by 1, y by 0, z by minus 1. Then the eigenvector, third eigenvector comes as 1 0 minus 1. So this is the eigenvector for eigenvalue lambda equals to 3. Now eigenvector, first eigenvector is 1 2 1, and x2 is 1 minus 1 1, and x3 is 1 0 minus 1. Now here you need to check whether x1 x2 x3 are pairwise orthogonal or not. So now to check this, we have seen the condition as x1 x2 transpose it should be equals to 0, and x2 x3 transpose equals should be 0, and then x3 x1 transpose should be equals to 0. So by these two, so when we multiply them, 1 into 1 is 1, 2 into minus 1 is minus 2, then 1 into 1 is 1, then that comes as 2 minus 2 equals to 0. So this condition is satisfied. Then x2 and x3, then 1 into 1 is 1, minus 1 into 0 is 0, and 1 into minus 1 is minus 1. So this also is 0, and this condition is also satisfied. Then x3 x1 transpose equals to 1 into 1 is 1, 0 into 2 is 0, minus 1 into 1 is minus 1, and this comes also 0. So three conditions are satisfied. Then we can write a statement as the three eigenvectors are pairwise orthogonal. Now after after checking whether they are pairwise orthogonal or not, then we go to the next point as normalized eigenvectors. So we have to find out the normalized eigenvectors. First, if x1 equals to 1 2 1, this is the first eigenvector, we need to find out norm x1. So we have discussed norm x1 nothing but under the root of 1 square plus 2 square plus 1 square. This gives the norm of x1. Then that equals to 1 plus 4 plus 1, that is root 6. Then here we need to find x1 by norm x1. x1 by norm x1 nothing but here we have to write in the form of matrix as 1 by under the root of 6 is the first element, 2 by under the root of 6 is second element, and 1 by under the root of 6 is third element. So this is the x1 by norm x1. Now in second, if x2 is equals to the second eigenvector 1 minus 1 1, so norm x2 is under the root of 1 square plus minus 1 whole square plus 1 square, and that equals to under the root of 1 plus 1 plus 1, that gives us root 3. Then here x2 by norm x2 is, So each element is divided by this norm x2, 1 by under the root 3 minus 1 by root 3 and 1 by root 3. So this is what x2 by norm x2. Finally, if x3 is equals to the third eigenvector, we got it as 1 0 minus 1, then norm x3 comes as under the root of first element square, that is 1 square plus 0 square and minus 1 whole square, that equals to under the root of 1 plus 0 plus 1 equals to root 2. This is what norm x3. Then x3 by norm x3 equals to, each element is divided by root 2. Then 1 by root 2, 0 by root 2 is 0 and minus 1 by root 2. So this is what x3 by norm x3. So we got x1 by norm x1, x2 by norm x2 and x3 by norm x3. Now here we need to find out the normalized model matrix P. Normalized model matrix P, that is, we know that P is equals to x1 by norm x1, x2 by norm x2 and x3 by norm x3. This is what normalized model matrix P. So here nothing but all the values whatever we got, we have to write in a column wise. So that P is equals to, the matrix comes as, so here 1 by under the root 6, 2 by root 6 and 1 by root 6 should be written in the column wise. That comes as 1 by root 6, 2 by root 6 and 1 by root 6. Then here in second we got x2 by norm x2 as 1 by root 3 minus 1 by root 3 and 1 by root 3. Right in the second column, 1 by root 3 minus 1 by root 3 and 1 by root 3. Then third column comes as this x3 by norm x3, that we got it as 1 by root 2, 0 minus 1 by root 2. So this is what normalized model matrix P. P transpose. P transpose nothing but rows, changing the rows into columns or columns into rows. So changing this row, writing this row in column, we get it as 1 by root 6, 1 by root 3 and 1 by root 2. Then second column, second row as second column, that is 2 by root 6 minus 1 by root 3 and 0. Then third row as third column, that is 1 by root 6, 1 by root 3 and minus 1 by 2, root 2. So this is what P transpose. We know that here P transpose A into P equals to D. So we had to prove this. P transpose matrix 1 by root 6, 2 by root 6 and 1 by root 6, 1 by root 3 minus 1 by root 3, 1 by root 3, then 1 by root 2, 0 minus 1 by root 2. P transpose into matrix A. Matrix A was 3 minus 1, 0, minus 1, 2 minus 1, 0 minus 1, 3. This is what matrix A. Into matrix P. P matrix is 1 by root 6, 1 by root 3, 1 by root 2 and 2 by root 6 minus 1 by root 3, 0, 1 by root 6, 1 by root 3 minus 1 by root 2. This is what the normalized model matrix P. We have to prove this equals to diagonal matrix D. So here this is equals to diagonal matrix. We know that diagonal matrix nothing but lambda 1 0 0, 0 lambda 2 0, 0 0 lambda 3. So lambda value first we took it as 1, 0 0, 0 4 0 and 0 0 3. So this equals to our diagonal matrix D. So P transpose into A into P equals to diagonal matrix D. One more canonical form, that equals to Y transpose D into Y. So Y transpose. So Y here, Y nothing but a variable matrix in terms of Y1, Y2, Y3. So Y1, Y2, Y3 into our diagonal matrix is 0, 1, 0, 0, 0, 4, 0 and 0, 0, 3. This is our diagonal matrix into the actual Y matrix is Y1, Y2, Y3. So transpose of this Y becomes as this. Now that equals to 1 into y1 square. So directly we can write it as here 1 into y1 square, 4 into y2 square and 3 into y3 square. So this gives us the final canonical form 4y square plus 3y3 square. So this is our here y1 square plus 4y2 square plus 3y3 square. So this is our final canonical form, and that will be of the form we can find it by using this Y transpose D into Y, where D is a diagonal matrix, Y is a variable matrix in terms of Y1, Y2, Y3. So when you multiply these three, we get it as this equation. So this is a canonical. So the canonical form of the given quadratic form is y1 square plus 4y2 square plus 3y3 square. So this is the canonical form of the given quadratic form. Then here the rank. So rank comes as the number of terms in canonical form. So there are 3 terms in this canonical form, as here y1 square is one term, 4y2 square is another term and 3y3 square is another term. So there are 3 terms. The rank comes as 3. Then they asked us to find out the index. So index nothing but number of positive terms in this canonical form. So number of positive terms, here all are positive terms, so the index also comes as 3. Signature, we know the signature nothing but number of positive terms minus number of negative terms in canonical form. That equals to number of positive terms are 3 minus number of negative terms are 0. 3 minus 0 is 3. So signature also comes as 3. And nature nothing, nature is positive definite, as all are the positive terms. The condition for positive definite, we know that R should be equals to N and S should be equals to N, or we can tell it as if all the eigenvalues of A are positive and they are non-zero. So eigenvalues was 1, 4 and 3, as they are positive and they are non-zero. So we can tell in this way, or R is equals to N and S equals to N. R nothing but rank, that is 3. N nothing but number of variables are 3. And S nothing but index. Index also we got it as 3. Then 3 number of variables are 3. So this condition is satisfied. Then the nature is positive definite. Then next it comes as x is equals to py, that is x nothing but this variable matrix in terms of x, y and z, and the p nothing but normalized model matrix 1 by root 6, 2 by root 6, 1 by root 6 and 1 by root 3 minus 1 by root 3, 1 by root 3, 1 by root 2, 0 minus 1 by root 2 into y matrix we know in terms of y1, y2 and y3. So when you multiply these two, so finally we can write it as x is equals to first element 1 by root 6 into y1 plus 1 by root 3 into y2 plus 1 by root 2 into y3. This is what our x. Then x is equals to this row into this column gives x. Then y is equals to 2 by root 6 into y1 minus 1 by root 3 into y2 plus 0. Then z equals to 1 by root 6 into y1 minus 1 by root 3 into y2 minus 1 by root 2 into y3. So this is what our x, y and z. This is nothing but transformation. So we have converted the or reduced the quadratic form into canonical form, and we have found the rank and index, signature and nature of the canonical form or quadratic form, and then transformation x is equals to py. So in this way we will solve the problem and reduce the quadratic form to the canonical form. Thank you.